Alright, welcome back to Organic Chemistry. Let's take a look at ethers. As you surely remember, an ether functional group involves two carbon groups attached to an oxygen. Structurally, ethers are related to alcohols and to water in that they've got that oxygen with two lone pairs and two bonds and the bent geometry. But they're different in that ethers don't have that hydrogen. And therefore, while they can act as hydrogen bond acceptors, they cannot act as hydrogen bond donors, and that will affect some of their properties. Some quick naming. There's two ways of naming ethers. Kind of the older way, which is still very commonly used, just involves taking an oxygen with two groups attached, naming those groups and calling it ether. For instance, this first one, oxygen, has two carbon groups, two ethyl groups attached to oxygen, and so it's called diethyl ether. This second molecule has an oxygen with a methyl and a sec-butyl. Sec-butyl is a four-carbon chain with a connection at the second position over. And this third one has an oxygen with a methyl and a phenyl. The systematic naming rules say pick out the longest continuous carbon-carbon chain. So in the first case, the longest chain has two carbons, so there's an ethane. But there's an ethoxy attached, that is, two carbon and an oxygen group attached. And so that guy would be ethoxyethane. The second molecule, the longest carbon-carbon chain is four carbons, butane, and there is a methoxy, and we have to say that it's attached at 2 because there's a couple of possibilities here. And finally, methoxybenzene. There are some trivial names. The most, for us, let's just mention the fact that this first molecule on the left is sometimes just called ether. Both in lab, if I ever refer to just ether, dissolve it in ether, I mean diethyl ether. If you hear the word ether outside of organic chemistry lab, you're probably specifically talking about diethyl ether. Recall, it's kind of similar to if you hear alcohol outside the realms of organic chemistry, you specifically mean ethanol. And finally, this molecule on the right, methoxybenzene, has a trivial name of anisole. Okay. Ethers, because they cannot hydrogen bond with each other, remember you need both hydrogen bond donating and accepting groups to have hydrogen bonding occur. They have pretty much low boiling points, and they're very comparable to alkanes. Of similar size and shape, they have very similar boiling points. Also, like alkanes, ethers are pretty much insoluble in water. Except for tetrahydrofuran, THF, that's kind of a special case. Otherwise, these things really don't dissolve in water, and as you've seen in lab, they form two separate layers. Generally, this is a less dense layer, right, in a separatory funnel. Now, while ethers can't hydrogen bond with each other, one thing they can do is donate electron density to things that need them. For instance, a Grignard. Grignards are generally insoluble in organic solvents, in nonpolar organic solvents, like, say, hexane. Grignards don't dissolve because they've got such polar bonds. They behave like ions. They really don't dissolve. If you put if you put Grignards in, say, water or an alcohol, sure, they'd dissolve, but they'd react very rapidly because those are proton donors. On the other hand, ethers dissolve Grignards, and the way they do it is by the lone pairs on the oxygen interacting with the magnesium and solvating it. And since the Grignard interacts with the solvent, it dissolves. This idea goes a step further with the crown ethers. The crown ethers are cyclic molecules that involve several ethers, and there's different crowns of different sizes and shapes. But they've got a hole in the middle with a lot of lone pairs around that hole. And things that are electron poor might fit in that position. Like, for instance, lithium, sodium, and potassium ions. And specifically, those three ions will fit very well in these three crown ethers. And because these crowns are different sizes and shapes, and the lithium, sodium, and potassium ions are different sizes and shapes, the lithium ion fits best in the first one, but not the other two. It doesn't fit so well in the other two. The sodium fits best in the middle one, but it's too big to go in the first one, and it kind of rattles around in the third one, so it doesn't fit as well. And potassium's too big to fit in the first two, but it fits well in the third. This was used in a really interesting experiment. Imagine a tube that's open at each end, but it's shaped like a U. So you can pour a liquid down here, and it would kind of sit there. And let's put a dense organic solvent like chloroform or dichloromethane down here. And then let's carefully add water to each side. And since these don't mix, this will form separate layers where the aqueous phases sit on top of the organic phase. Now let's add a bunch of lithium ions to this side. And let's look over here. You know what? No lithium ions. Because lithium ions don't dissolve in dichloromethane. And so it's not like the lithiums that are over here are going to somehow get over here. Okay, now let's change our experiment. Down here, let's put a bunch of this crown ether. Let's dissolve a bunch of that. That dissolves in dichloromethane. And have that floating around in here. Now, all of a sudden, I'm going to start seeing lithium show up over here. Why is that? The crown ether doesn't really dissolve in the water, but when it floats over here, it kind of comes into contact at the edge with lithiums that are kind of in here, in this edge. The lithiums will go in the crown, and the crown will float around in the organic phase, carrying the lithium around, and until eventually it comes here and it dumps it out. This work, and related work, won the Nobel Prize for Pedersen, Lane, and Cram. And it's really important for understanding how things move around in the body. For instance, this compound, nonactin, looks a lot like a crown ether. It's a cycle, and it's got a bunch of oxygens pointing towards the middle. Notice some of these functional groups are ethers and others are esters, but regardless, it kind of has that same idea. And in this picture on the right, we see that nonactin will kind of surround a metal ion, this in particular is a potassium ion, and interact with it, just like the crown ethers that we saw. And in the body, nonactin exists biologically, and it will carry ions across a nonpolar medium. For instance, if this is the exterior of the cell is aqueous, and here's the interior of the cell, aqueous, but the cellular membrane has this nonpolar component. And so if there was lithium ions out here, they would not just simply diffuse across this because they wouldn't dissolve in this region. So lithium ions would just stay out here. But nonactin can act as a carrier, where it floats to one side of the membrane, it grabs that potassium. This grabs potassium, and pulls it across the membrane and then drops it off on the other side, just like that YouTube experiment. Alright, well, let's talk about the chemistry of ethers. How do you make them, and what do they do? Well, there's only a few ways to make them, and these are complete review, so I'm not going to go through these in detail. If I took an alcohol and I treated it with base, I would deprotonate it, make the O-, the alkoxide. That's a strong nucleophile, and that will do an SN2 reaction on, say, a primary alkyl halide to give an ether. If I had a tertiary alkyl halide, and I dissolved it in an alcohol, well, what would happen? Well, leaving group would go away, making a carbocation, and then, well, solvent's a weak nucleophile, that'll come in after loss of a proton, giving an ether, an SN1 process. Also, in a mixture, you would also get some E1 process as well. And then finally, if I had an alkene and I treated it with acid and some weak nucleophile, pi bond would reach out to the acid, we'd form a carbocation intermediate, and then the nucleophile would come along, and after deprotonation, in this case, since our nucleophile was an alcohol, we make an ether. So these are ways of making ethers, and these are all ones we've seen more than once before. What do ethers do? Well, pretty much nothing, which is really great for solvents, because when you're running a reaction, you don't want your solvent to take part in the reaction, generally. And so ethers are great because they dissolve a lot of things, but they don't react with a lot of things. One thing that they do is they will undergo mineral acid cleavage. The mineral acids are HF, HCl, HBr, HI. If I treated an ether with HCl, it would break that ether down and return alkyl halides in its place. You generally have to heat this thing up because there is some bond breaking that takes some energy. But let's walk through the mechanism. It's pretty straightforward. HCl is an acid. It's the source of proton. Oxygen lone pairs can grab that proton, but now we want to break one of those three bonds. If I deprotonate, well, I'm back where I started. No harm, no foul. If a chloride came in and did an SN2 type reaction, we get an alkyl chloride and an alcohol. That alcohol can react with another equivalent of HCl. Oh, here we've got water, which is a great leaving group. Let's have it leave. And if a chloride came in, we'd get product. Notice that depending on the carbon groups on either side of the oxygen, these steps could be more SN2-like, like in the first step I showed, or more SN1-like, like in the last step I showed. But in either case, these are substitution reactions where chloride is the nucleophile, and you ultimately get alkyl chlorides. But that's pretty much it for ethers. They don't do much else. I'll mention a couple of related things. Siloethers are silicon analogs. Instead of carbon, oxygen, carbon, you make carbon, oxygen, silicon. So if I treated an alcohol with a base and trimethylsilochloride, TMS chloride, I'll make a trimethylsiloether. This is sometimes abbreviated as a TMS ether. These siloethers react with fluoride agents. HF and tetrabutylammonium fluoride are both sources of F-. And if I treated a siloether with TBAF or with a fluoride agent, they would cleave the siloether, leaving an O-, which would get protonated to make OH. I'll show the whole mechanism in a moment. There's other ethers as well, other siloethers as well. Let's not belabor that, but there might be reasons why, in given situations, you might be interested in one or the other of these types of siloethers. I want to go through this mechanism just because it's a little bit different than things we've seen. This is actually an associative substitution reaction. That is, the fluoride comes in and adds to the silicon, and the silicon goes hypervalent. It violates the octet rule, but that's okay for silicon because we've got d orbitals. It's in the third row of the periodic table. You would never do this on carbon, and that's why when we talked about substitution in terms of carbon, nucleophilic substitution in terms of carbon, there was only two possibilities. Leaving group goes away, and then nucleophile comes in, or those two things happen simultaneously. Here with silicon, we can have the process where first nucleophile comes in, and then leaving group goes away. After protonation, we get an alcohol. Another topic that's related to ethers is thioethers, also known as sulfides. And these are the sulfur analog of ethers. A thiol, in this case 2-butane thiol, is like an alcohol in that if you deprotonate it, you make a conjugate base, which will do SN2 reactions. So this is like the Williamson ether synthesis, but it's a thioether that you made. Like ethers, you can cleave them with mineral acids, but there's other reactions as well, and the interesting one I wanted to mention is if you treated a sulfide with hydrogen and rainy nickel, in a mechanism that likely involves radicals, you cleave all the carbon-sulfur bonds and you replace them with carbon-hydrogen bonds. We'll come back to this reaction a little later. But pretty much that's it for ethers. They don't do much, and the ways of making them are things that we've already talked about multiple times, and so we don't have to spend a lot more time on ethers. Alright, thank you. And I'll see you next time when we talk about epoxides.